Using that method, we have find the expression of the PDF of sum of two random variables, z equal x plus y, and we show that f z of z is equal to integral over one of them, let's say x from minus infinity to plus infinity of f x y of x is equal to z minus y and y dy. So now in this video we want to see how this expression can be simplified if the random variables x and y are independent. In other words, we are interested to find the distribution of the sum of independent random variables. So far, for the sum of any two random variables, we find that the distribution of the sum can be written in forms of this integral. Now, if we assume that the two random variables are independent, these fx of x and y of x and y is decomposed into fx of x times fy of y. Just we could substitute there and then obtain a theorem which is equal to this one. So if you do that, you quickly get this one, which is a convolution. So if you add any two random variables x and y, you get z. And then if they are independent, they could be characterized with fx of x as distribution, fy of y. So then you need to convolve fx of x, fy of y. So if you do convolution here, I put here, by these I mean convolution, not multiplication. And convolution means this integral, okay? It gives you fz of z. So let's say instead of product, put some like a star. So so denoted by this. This is convolution. Convolution is a type of product, but an integral is involved in it. Let us have one example. Assume that x and y are independent and x is uniformly distributed over an interval of a and b. That means that the PDF, let's say this is a, this is b, and the PDF is constant because this area should be equal to 1. This value should be b minus a. And let us assume that, let's say, y is uniformly also distributed over the same interval, so it has the same PDF. We want to find the distribution of these guys. So let's say this is C and D. So for these two assumption means that one of them has a distribution over A and B. This is fx of x, and fy of y is, let's say, distribution between C and, let's say, D. So you have another flat distribution. This area is equal 1. This area is also equal 1, fy of y. Now, if you say z equal to x plus y, intuitively we know that the maximum value that x can take on is b. Okay, so for value of z, so I get, because the maximum value of this is b, maximum value of this is d, so the maximum value I get is b plus d. And the minimum value that x can take is a, minimum value that y can take is c, so the minimum value of the sum is equal to a plus c. So my distribution is 0 outside of this interval. So I could quickly say that fz of z shall be equal to 0 if z is smaller than a plus c, or z is bigger than b plus d. Okay. So using the convolution integral, if you convolve these two rectangular pulses, you will find a trapezoidal, because you need to flip these over and then slide it using your undergraduate thing. And you see that you would get the starting point of your distribution for Z is A plus C, which is the minimum range of X, minimum range of Y added together, and the maximum. So the support of your distribution is going to be this interval, which is minimum of A plus D and C plus B, and a maximum of this. So, and then these 2 points which you have is because you have 2 numbers here, A and B, and you have 2 numbers C and D. So if you combine them, you will have 4 points, 4 possible points. And then you get the corners of these trapezoidal. So the sum of the PDF of 2 independent uniformly distributed random variables will have a trapezoid. Sometimes if these points and these points are equal, then you will have a triangular distribution.